Alright, let's start out Lesson 6, Covalent Bonding Part 2. Just as a reminder, a covalent bond is a bond that exists between the nuclei of two different atoms that are sharing a pair of electrons. Now, in this particular lecture video, and in others that will come, we are going to represent covalent bonds by using a dashed line in between the atoms that are forming that bond. For instance, let's say we're going to form a bond between two hydrogen atoms, like in H2O. We're going to take one hydrogen and put a dash in between both hydrogens, and that dashed line represents a covalent bond, or in other words, the two electrons that are being shared between these two hydrogen atoms. All right? And anytime you see a dashed line between those, you absolutely have a covalent bond, and each dashed line always represents two bonding electrons. All right, now in this second half of Lesson 6, we are really going to focus on polar versus nonpolar covalent bonds, what they mean and how they're formed, and the dramatic implications to polar-nonpolar bonding. So to begin with, we're going to start out with nonpolar bonding and work our way into what a polar bond is in just a moment. So a polar or a nonpolar bond, okay, so a nonpolar covalent bond is going to occur when you have two atoms that are sharing electrons and they have similar or nearly identical electronegativity values. So if you have these two atoms that are sharing electrons and their electronegativity values are identical, then they're going to be nonpolar. What that simply means is that the electrons that are being shared will be shared equally between the two atoms. All right? Whereas on the flip side of this, a polar covalent bond means that the shared electrons between the different atoms have different electronegativity values. And the results of having different electronegative values means that the electrons are not going to be shared equally between the two atoms. Simply said, then, that the atom that has the highest electronegativity value will spend more time with the shared electrons than the other atom will. All right? So that's really the difference between a nonpolar covalent bond and a polar covalent bond. So just think of this: nonpolar covalent bonds, a equal sharing of electrons, and a polar covalent bond, there's not going to be an equal sharing of electrons. All right? Now, when we have a polar covalent bond, what's going to happen is there's going to be a buildup of partial negative and positive charges. And this will literally create two oppositely charged poles. And we'll demonstrate all of this in just a minute. All right? So one of the ways that I think you can look at covalent bonding is that when the two nuclei of the different atoms are sharing a pair of electrons, there's a tug-of-war match that's going on between those two nuclei. Both nuclei want those electrons, and they want them very badly. And so they're going to be pulling on those electrons, tugging on them with every force or might that they have. And each of those atoms, even though they're sharing them, is going to try to win this tug-of-war match. So, for instance, you can think of this one here where we got two hydrogen atoms playing tug-of-war with these two electrons here. Now, whoever wins the tug-of-war match is the atom that has the highest electronegativity value. But in the case of hydrogen, because they're the same atoms, both these hydrogen atoms are going to have equal electronegativity values. So they're going to pull on the electrons with the same force. And so neither atom will win, and therefore there's going to end up being an equal sharing of the electrons, and we form a nonpolar covalent bond. However, if we have a bond between two atoms that do not have equal electronegativity values, such in the case of this chlorine atom and this hydrogen, this poor hydrogen atom is pulling with all its might, but does not have the strength that the chlorine atom has. The chlorine atom has a greater electronegativity value, so therefore it's going to win the tug-of-war match, and the shared electrons are going to be spent more time with the chlorine atom than it will be with the hydrogen atom. So we simply say that there's an unequal sharing of electrons, and we have a polar covalent bond. All right. Now, to look at this in terms of electron density. Now, remember that in Unit 2, when we talked about the quantum theory or the wave mechanical model, we talked in terms of electron densities. And an electron density, if you recall, is just simply the probability of finding an electron in a region. And so the higher the electron density is, the more probable we're going to find an electron that occurs in that region. So what we find here is this is an electron density model here. And so we have a hydrogen and a hydrogen, and then we have a pair of electrons that are being shared between those two hydrogen atoms. And actually, I'm going to erase this here. So I'm going to just show the two electrons that are being shared. Now, because this model here, it literally shows us where the electron density is found at. And because there seems to be an even distribution of electron density around this, you can see all around here there's an even electron distribution as the same shape. It tells us that the electrons are going to be found evenly distributed. In other words, there's going to be an equal sharing of electrons here, as composed to the electrons that are being shared down here. You can see that there's an uneven distribution of electron density. Most of the electron density is found over here where the chlorine atom is, okay? Which shows you that there's an uneven shape. It's a bigger bulge here and a smaller bulge right there. It just simply says there's an unequal distribution of electron density. And so the shared electrons between the hydrogen and chlorine, most of the time those electrons are going to be way close to the chlorine. That creates a higher probability of the electrons being around chlorine, indicated by the higher electron density there. All right? So hopefully you kind of get this idea. All right. Now let's look at these captions here. So two hydrogens have identical electronegativity values that results in equal sharing of electrons. Electron density is equally distributed, so there will be no oppositely charged poles. Okay. And we'll talk about those charged poles in just a second. Okay. Whereas in the hydrogen-chlorine covalent bond, there's an unequal sharing of electrons. Chlorine has a higher electronegativity value than hydrogen, and this results in an unequal distribution of electron density. This unequal distribution of electron density then creates two oppositely charged poles. The higher electronegative atom is assigned a partial negative charge because the electron density is much higher. All right. So we can show this again. The electrons are going to mainly be over in this area, which is indicated by the green, because that's where there's a higher electron density is in that green area. And so there's going to be a partial, and this sign that I'm writing here is called delta. It's a lowercase delta, which means partial, and I'm going to put a negative charge, because mainly on this this side of the molecule, or this side of the bond, there's going to be a higher electron density, which therefore makes it negative. And on the other side, by hydrogen, it's going to be a partial positive charge. Now this essentially creates two poles, a positive pole and a negative pole. And that's what we're talking about, is creating these oppositely charged poles. All right, now let's look a little bit closer at this idea of uneven electron distribution of charge. If we have an unequal distribution of charge, then we create what is known as a dipole. All right, the word di means two, and then pole. So we're going to have two poles, and those two poles are going to be created because of the difference in electronegativity value. And the size of the dipole increases with an increasing difference in electronegativity values. So in other words, the bigger the difference in electronegativity, the bigger the dipole is going to be, and the more partial negative or partial positive we're going to have. Now, to represent a dipole, we use an arrow notation, right? An arrow will always be pointing towards will be pointing away or from the partial positive towards the partial negative charge, and that is pretty much the convention of what we use. So you can see down here our arrow. Oops. The arrow notation here is pointing to the partial negative and the partial positive away from it. Okay, this is the negative pole, this is the positive pole, and so we end up having a dipole that is formed. All right. Now, to indicate that this is a dipole too, we use an arrow with a line down like so to give us that an arrow notation that this is a dipole that we're looking at. All right, so here's a clearer picture, I think, of this whole idea. Okay, so you can see, going back to our electron distribution or our electron density, that there is a greater electron distribution over by the chlorine. It's much bigger, fatter area. Okay, and so therefore we're going to call this a very electron-rich area, which gives it a partial negative pull. Over here, where the hydrogen is, there's not as much electron density, so the probability of finding those bonding electrons over by the hydrogen is not as likely as it is by the chlorine. So we're going to refer to this as an electron poor region, and so therefore it creates a partial positive charge. Therefore, if we were to draw an arrow, the arrow should be pointing towards the chlorine with a line down, indicating that the chlorine is more electronegative than the hydrogen, and that the chlorine has a partial negative charge versus the hydrogen. All right? All right, the last thing we're going to look at is some colored diagrams of electron density. All right, so where you see the red at, so the red is and you might want to write this down because you're going to see these models a lot, and this is traditional. So where you see the red, where you see the red is where it's going to be have a high electron density, or it's going to be very much electron rich. So we're going to say high electron density. Okay, is where we see red. Where we see blue, blue is going to be low electron density. And then we have kind of green, and green is kind of an even electron density. It kind of has an in-between. It's pretty much evenly distributed. And then we also have a little bit of yellow, and the yellow tends to show that there's a little bit more electron density there. All right, so here we got lithium hydride, hydrogen, and HF. And you can see that with hydrogen, there's an even amount of electron density. It has that green, even distributed electron density out. And so hydrogen is definitely a nonpolar molecule. HF, we have a very high electron density over by the fluorine, and not so much over here by the hydrogen. So the hydrogen, so if I was to actually draw a covalent bond between HF, right? Most of the electron density is over by the fluorine, and that's giving the fluorine a partial negative charge and the hydrogen a partial positive charge. All right, so we can kind of erase that so I can make it a little bit clearer here with all of this. All right, so again, this is partially negative, or this is high electron density with the red, or very electron rich. And over here is partially positive. It's electron deficient or electron poor, with very low electron density. So hopefully you get that idea. Whereas the hydrogen has even electron density, so there is no dipole. So there's no partial or negative charge there. Lithium hydride is going to be highly electronegative, or highly electron dense over on the hydrogen side, and on the lithium side it's going to be very low electron density and very positive. Okay, so hopefully you kind of get the idea of the difference between polar and nonpolar here in electron density. So in summary, really quick, a compound or a covalent bond will be nonpolar if the two atoms that are sharing electrons do so equally, meaning that there is an equal electron density or distribution of charge, and both atoms have the same electronegativity value. A bond will be polar if the two atoms have different electronegative values. Therefore, there's an unequal sharing of electrons, and one of those atoms is going to have a higher electron density around it than the other atom, and therefore we're going to create two oppositely charged poles, or a dipole. And the dipole that is partially negative is where the most electronegative atom is, or where the highest electron density is, and the partial positive pole is going to be where there's low electron density. All right, so that's it in a nutshell. Study this. This is really super important. If you need to go and re-look at this lecture video, do so. Study your notes really well. Come and ask me questions if you need to. But that is it for right now.